example number 4, we're going to deal with non-negative periodic functions. So we're going to say the absolute value of tangent x, and I'm going to make these a little thicker so you guys know that they're absolute value brackets. And then the absolute value of sine of x. Now you should almost, I like to graph this a lot so you guys can kind of see what they look like. Tangent. Does anybody remember what tangent looks like? Can you make the little wavy motion? Yeah. So how's it come in? Does it come from the bottom or go to the top?
Top.
The bottom. Does that make parabola?
Yeah. Does it go through the origin?
No.
No.
No. So what's the period of it? Do you guys remember?
Zero.
Pi. Good. So and where does the first little line cross the x-axis?
Never.
Well, it's half pi. So if it has a period of pi, so it kind of comes in like this,
Oh.
and then the next one is like this, and they never really cross. In fact, this is not the best drawing, but it kind of looks like this. Now, when I say the absolute value of tangent, what does that do with the corresponding y values?
Make some no negative.
No negative. So all these negative values, what happens to them?
They go away.
No, they don't go away. They become
Positive.
positive, which causes them to
Cross.
flip off. So you're going to get something like this, kind of. Okay? I'm thinking. Now, the other thing is, for sine of x kind of does one of these deals, right? It kind of goes with a period of 2 pi, the range of 1 to 1. Now, what's going to happen here when we take the absolute value of that?
Positive.
It'll
All
flip
the
them
same
up
thing.
to
The
the top.
negatives will flip up. So you'll get a graph that kind of looks like this. Now let's see, and then we're going to talk about, is it periodic, or what is the, is it periodic or not periodic? So I'm going to graph the absolute value of sine first. So let me clear this out. I shouldn't have cleared that out. That was actually what I needed. So catalog, or wait, what's the quickest way? Math? Num. There it is, boom. And then we want sine of x. All right, we should have done tangent first, but that's okay. Let's graph sine. Hey, I'm pretty smart.
It looks like they're bouncing.
It almost looks like sine of x squared, or sine of x, the quantity sine of x squared. Except we have a little cusp here.
What's a what?
So it's like a little corner.
Oh.
So we guessed sine of x right, correct?
Yep.
So that's good. That's good. Now let's look at tangent. Well, let's do these one at a time. Our goal is to determine if it's periodic or if it's sinusoidinous, and so we're going to analyze that.
I have a question. Can it be both?
Yeah, if it fits. So sinusoidinous means that it looks like a wave. That's the easiest way to describe it, like a uniformed wave. I'm not saying that it's wavy. I'm saying that it is a uniform wave. Is that a uniform wave?
No.
No. So it's not a sinusoid.
But it is.
Is it periodic?
Yes.
So if I go into the table of values, right? If I go into the table of values and I look at it, the pattern does repeat after a while. And we just have to determine when that pattern repeats. So we've got to go back to the first 0, which is at 0, 0.
Mm-hmm.
And when does the pattern repeat? At pi. So the periodic, or the periodicity of this would be 1 pi. And so let me read what the book says. It says, whenever sine of x is defined, so is sine of x, the absolute value of sine of x. The domain of G is the same, all real numbers, but because of the negative values being flipped up to positive, then everything will be positive. So the period will be 1/2, or pi. All right, so that's that one. Let's go now and do the absolute value of tangent. So I'm just going to put tangent in here.
I have a quick question.
Yeah, lay it on me.
How do you get for in your table the x values to not be whole numbers?
Oh, you.
Oh, I'll show you. I'll change it in a second.
In the table second.
That's a great question.
How do you get to that?
Also, wait.
So the question that she asked me was,
I found it.
no, sit down. I'll explain. I'm recording a video, and I have one microphone. The question was in her, this is what she's getting. She's getting a weird, it's not weird, but this is how the default is set up. So when you look at the table of values, she's getting this, where all of her x values are 1, 2, 3, 4, 5 or integers. And so because we're dealing with trig functions and I'm in radian mode, I want some variation of pi. So the way that we change that is we would hit second, table set. Now I want to start at 0.
Yes.
But this delta table equals 1, that determines what increment for x that I count. So it's really delta x, how much I change by. And so earlier I had it at pi divided by 6, but I said usually pi divided by any value would be helpful. So I'm going to do pi divided by 3, just so you guys can see that it changes a little bit. Now when I hit second table, I can see rather quickly the pattern repeating itself. So it still doesn't change anything. My period repeats every pi, right? So at 6.28, I've got 0 again. And notice that these numbers are the same. And if I wanted to put more x values in between, I could do pi divided by 10, pi divided by 5. But usually we do pi divided by 3, pi divided by 6, and pi divided by 4, or pi divided by 2. Any other questions? No? Okay. All right. So where I was going with this is now that we look at this, would you say that this is periodic?
Yes.
Well, we almost have to because that's what the table of value shows. But when I look at the graph, is that sinusogenous?
No.
No, it's not a sinusoid. Or sinusoid. It's not a sinoid function. Oh, I can't talk today. You know what I mean.